So 4.4 is all about the definite integral and the fundamental theorem of calculus. So I would really suggest that you go through the whole process that I have on this on the worksheet and work through finding the actual area under these curves. So if you're in my calculus class, the first 1 through 4 are the same as 5, 6, 7, and 8. And you should have an answer for 5, 6, 7, and 8. So what we're going to do is what the definite integral is. If you follow up here, you're going to do the antiderivative, and then we're going to take the top value, our final, minus the bottom value, our initial. Alright, so let's see what we get. So the antiderivative of x, that is a polynomial, so it's x squared over 2. Now we're not going to do plus c, we're going to do this fun thing, 0 to 4. Now I've got brackets in here because I couldn't figure out how to make the Microsoft Word do that little slash there very easily. So all we're going to do is we're going to plug in our top. So 4 squared divided by 2 minus our bottom, which means 0 squared divided by 2, and we end up with 16 divided by 2, or 8. If you do your right-hand Riemann sums, add up an infinite number of rectangles, go through the whole process, you should get the exact same answer. Now, you'll notice that there's no c value. Now, when you're doing a definite integral, you don't do a c. So this is getting at the area under the curve. When you do the area of the curve, expect a number. Again, the area of the curve may represent something else entirely. This antiderivative might be velocity, and then you get position. And so you're talking about like total displacement. But, however it goes, don't put a plus c. If you had a plus c over here, you have a plus c, and over here you have a plus c. And they would basically cancel out. So that's another way of thinking about it. It's not quite as accurate, but still decent. All right, let's try another one here. So all we got to do is we do our antiderivative. So x squared minus 5x. Then we plug in our bounds, 3 and 1. So 3 squared is 9 minus 15. That's our top bound minus our initial, 1 minus 5. And be really careful about your signs. Make sure it's a minus between the two. So plug in your top to both your x's, plug in your bottom into both your x's, and don't get this part wrong. So this is negative 6 minus negative 4. So negative 6 plus 4, or negative 2. Now again, if you want to check any of these, you can always plug them in your calculator. Now, if you don't, I showed on the different one how you can use the newer operating system to find these. It's actually kind of like right here on the screen here. So again, on the newer operating system, you can hit alpha window, and then there's number 4, function integral, and you just make it look the way you want to. Now another way of doing this, and it really only works when you get a nice window from 1 to 3. If you're doing like 2,000 to 3,000, you gotta mess with your window a little bit. But you can do this graphically. You can go in your y equals, not off of y equals, let's quit out of that. Just regular y equals, put your equation in there, 2x minus 5, and we're just going to basically tell the calculator to do the area of the curve. So we graph it, and then you hit alpha trace, not alpha, sorry, get out of there, second trace, and you end up with number 7 here. Okay, it says lower limit. Well, we're going from 1 to 3, so my lower limit's 1. My upper limit is 3. Now, I know it says lower and upper. It's just how you want it to be. Initial and final. And then you see, it actually even fills in the area of the curve, and it gives you negative 2. So this works fantastic when you got a graph that's picture will just be in the window. If you got a weird graph or everything's huge, it's going to be kind of tricky to see it, but this will work on all of the calculators. And that's really it. Take your antiderivative. We'll bring this back up here. That's really it. You take your antiderivative, you plug in your top minus your bottom, and you get your value. Now, one of the things you might be asking me as a teacher if you're in my BC Calc class is, well, so why did we do all that area of the curve, an infinite number of right rectangles? Well, for one, it's good practice. It's a good thing to kind of work on and know what's happening behind all of that. Also, you're going to find a lot of the AP problems will either set up the summation, you have to realize the area of the curve, and then you can do this, or they'll give you charts, and you'll have to do the left Riemann sum, the right Riemann sum, on the trapezoid. And we'll see a bunch of those. There's a bunch later on in the packet too. But to do an infinite number of them, if you want the area of the curve, this is the way to go. This is how you really want to do it in the future.